I'm going to talk about the AI products that we've been building in residential real estate. I'll provide context and the business use case. And then I think we're in a really exciting time where we're actually in this stage where companies are able to build AI products and not just merely using AI tools. So my own career path, I graduated college in 2003 and got my PhD in 2011. Did two postdocs, and then went through the Insight Data Science Boot Camp in 2017. I started working as a consultant, mostly with media and digital streaming companies. And then I went on a stint in Weight Watchers and an app startup. And for the last 3.5-ish years, I've been at Rock 360, which is a real estate fintech company. And I'll describe the company shortly. This is our team. We have 13 members total currently. Half the team is remote, half are local, kind of all over the world. A few masters, few PhDs, all in astro, and a few team alumni with astro PhDs as well. The business context here is that we're a financial institution and we specialize in residential real estate investment loans. Okay, so these might be fix and flip investors who are looking to have found a property at a foreclosure auction, or maybe someone's kind of worn down property that's older, and then basically pitching it as an investment idea and said, hey, if you can lend me the renovation money, then I can flip this home for a profit and pay back the loan. There are also folks who purchase properties as rental investments and who need a business loan that's similar to a mortgage. And these are mom and pop investors. These aren't institutional. We don't deal with the BlackRocks of the world. These are folks that are kind of hustling and mostly sourcing properties and prospecting on their own. We also provide things like title and property insurance, and we can source properties and leads for investors as well, basically suggesting, hey, these might be interesting properties for your next deal. Okay. And real estate is a challenging data industry because the source of truth is analog. I think everyone in the audience has probably signed a lease at some point in their life, and leases can be complicated. If you ever have the misfortune of signing for a home purchase, it's literally hundreds and hundreds of pages of documents that you have to initial and sign. And the data is fragmented, even though much of the documents are technically public. They're recorded and digitized by individual county registrars. Information about the properties are handled by local agents. There's mortgages and loans are given out by hundreds of different banks and lending entities. There's nothing uniform about this data. There is no standard form for mortgage. There's no standard form for deed. Everything looks different. And last year, I spoke about how our company is using LLMs to facilitate document parsing, like things like, hey, who signed for this document? Or to normalize data from unstructured text. Is, as an example, is this house close to public transit, judging from the free form text in the property description. And today I'll speak about how we're building AI products that accelerate our business. And there's a difference that I want to highlight here between tools and products. An example of tools for the context of this presentation is things like the ChatGPT user interface or an Excel sheet or your own Python script, right? These are things that you individually can use to help your own workflow and maybe share with a couple of people, right? When we talk about products, we're talking about automation and orchestration. We're talking about scale. And because we're trying to automate things, right, we can't be debugging little errors that pop up, right, that might happen when you, right, load up the wrong number of columns in your Python script. So there has to be really robust error and exception handling. You have to deal with the edge and corner cases. You basically have to build a robust piece of software. And in my opinion, this is one of the main barriers to AI adoption today. It's the resource gap between institutions that have the resources to build this kind of AI software and those that can't, right? So a small company or medium-sized company or company that's not tech savvy might have individual employees using ChatGPT or Cloud or Sora or whatever, but there's no company-wide standardized tool that people can participate in to really drive the business forward instead of helping individuals. And another major barrier is business knowledge. Right? These tools need AI to be on autopilot, right? Because the AI is in the software backend. And if you have the AI hallucinating or saying incorrect things, then the business just can't use that. We can't have these examples of AI hallucinating imaginary papers or incorrectly mixing things or saying inappropriate things, like putting a tragedy next to some celebrity gossip in the case of like Apple News. You really need the AI to be doing all of the right things for people to be able to trust it and for the business to use it. And we have a few examples of AI products that I'll go through. One is the first one I'll discuss is document processing acceleration, and then live editing, outgoing communication. There's RAG-assisted search, and I'll describe what RAG is for folks who are familiar with that, as well as a research phase about interpreting property images using multimodal models. And then I'll lastly discuss a less generative AI example and more vector space and abstract vector space application about property comparison. So why is this important? Every real estate loan we make involves hundreds of pages of documents. We process thousands of loan applications every month. So the number of pages that people have to go through really piles up really fast. And not only are we processing millions of pages of documents on a regular basis, typical loan amounts are hundreds of thousands of dollars or even millions of dollars. So we cannot make errors, right? We can't have an AI or a human incorrectly say, oh yeah, this is good to go, and then have a $500,000 loan, backed by a property that's actually not worth anything. And these are just some of the documents we have to deal with. We have to deal with the actual loan document, which might be 50 pages, an appraisal document, which might be 50 pages, insurance policies, background checks, credit reports, purchase contracts, loan documents for an investor's past projects, articles of incorporations for their LLC entities, property descriptions that might be put up in StreetEasy or whatever. And all of these things have to be processed, and this is just a subset. So before we fund a loan, we need to verify that the pertinent documents are signed and initialed in the appropriate places, and we need to verify that every detail in that document is what we expect. So is the name, the person's legal name, are the property addresses correct, are the lawyers correctly listed? So these kinds of really tedious things, and in the itemized counts in the hundreds that need to be really consistent. And we've built a system to do this at scale. And it's basically a web app where a user is presented with a checklist of all the things that they need to verify, with an interface where the person can confirm or override the discrepancies, right? If someone says someone's name is Thomas Smith Jr. and it says Tom Smith Jr., right? Depending on the use case, the user might say, okay, that's actually okay. And then say override. This is built using, we use AWS Bedrock for this. So we have essentially a flow where whenever any document is uploaded or modified in our S3 bucket, this triggers a series of flows. We call a multimodal document classifier to figure out what kind of document we think it is. And then depending on the document type, we will then trigger the appropriate checks. We will extract information, and we will schematize it. We will upload it to our Snowflake instance. Then that Snowflake set of data is compared with our web app set of data to make sure that everything is consistent. And then this is fed into our analytics data layer, as well as our internal app. So this is a fairly, I'm not going to go into the details, but it's a fairly robust and intricate application. And again, this is something that, in my opinion, uh, is separating individuals using AI at businesses versus businesses using AI. Second example of generative AI that we're using is outgoing message QC. So we want to make sure that outgoing messages have a consistent tone, level of professionalism and localization, making sure that we maintain the meaning of industry jargon and abbreviations. Right, this can get pretty tricky for an out-of-the-box large language model. And we need to do this at scale, integrated within our own chat interface. And then we also need features for the users to say, okay, I'm going to accept this revision that's been suggested by the AI, or I want to edit this message some more, right? We've all had the experience of dealing with customer service agents who are either bots or who are folks based in the US or based in other parts of the world. And we've all dealt with people that might be unprofessional or might use slightly, they might use jargon or dialects that we're not entirely familiar with. And then we've all dealt with AI not understanding acronyms or jargon. So we want to solve for all of these issues so that people have a smooth and seamless experience dealing with messages coming from our company. This is a rough example. So this is on the top is an outgoing text message, right? There's acronyms. It's kind of brief. Please provide track record to verify experience. It's somewhat a customer reading that might have follow-up questions, right? So the AI kind of makes the message a little more polite. It interprets the acronyms and expands them. And it kind of expounds on the meaning of the last sentence. It's like, hey, please provide a track record to verify your experience. So this is an example of something, and this is something we developed in late September. A third example is retrieval augmented generation, or RAG. So this is something that a lot of companies are building where they have a lot of unstructured documents. So this is essentially vectorizing all of your unstructured data text or data images or pertinent documents, and then allowing your software to search this vectorized database so that you can ask questions about specific business transactions or business records. And you can think about this as like a really smart Google for your business, right? Not only is the chatbot or the search engine able to parse the semantic meaning of the text, it's able to do it in the context of your document trove. And it can do it in the context of images, in text. And this is, I think, one of the more hyped, but true to hype, I think, examples of generative AI that businesses are building. And we're, of course, as a company that deals with a ton of unstructured data, we're, of course, building this as well. This is something that's more in the research stages with multimodal vision models. And we're always exploring what's possible with generative AI and poking around with different tools, just because the landscape is changing so rapidly. So here the goal was provide images to the AI and ask it to ask it to output very specific things, like what is the room type depicted in this picture? What would you say is the condition that the property or the room is in? And tell us the reason why you think that. Also, from a list, provide us some features that you see in this image. And this is potentially a really impactful kind of tool for us because properties are unique, right? No two houses are alike, no two bathrooms are really alike, unless you live in a big apartment complex that's been recently built. And in our business, especially because the bulk of our business is around ground up construction or fix and flip homes, we expect to see a lot of weird things like bathrooms with holes in the wall or, kitchens missing sinks. We expect to see things that have been damaged by a storm. So it's really important for us to have a really flexible accounting if we want to have use AI for this purpose at all. It needs to be really flexible and robust because there's the industry, the business use case, it's just riddled with edge and corner cases. And here are just a couple of examples. On the left, you see the AI says, oh, yep, this is a bathroom. It's in pristine condition. And the reasoning is that the room appears to be clean and modern and so on. Then on the second image, the AI says this is a kitchen. The condition is heavily worn. The cabinets and flooring show significant wear and tear along with dirt and stains. And they list some of the other things that it sees. And this is still in the experimentation stage, but this could be something that's potentially really useful if the AI can, maybe the AI can catch things like damage that a busy human will miss, or they might notice things that are unusual about the property. It might be able to go through 5,000 images and pick out all the images that show examples of marble flooring, right? So there's a lot of different use cases to extract insights out of these kinds of images. This was kind of an interesting one. We were really surprised, actually, that the AI model was able to do this. This is random picture of a corner of a yard. And the AI said, oh, yeah, this is an outdoor image. It's heavily worn. And the reason I'm saying it's heavily worn is this AC unit appears rusted and there's overgrown grass and dirt. And it identified the stucco wall. It identifies this gas tank that's in the corner. We were actually really surprised that it was able to give this much amount of correct detail about this image. So again, this is something that we're playing around with one of our many research projects. And then the last thing I'll touch on is little less generative AI and more in the realm of advanced data handling. It's critical for us to understand the values of properties before funding real estate-backed loans, right? If a borrower comes to us and says, I bought this property for $100,000. If I do $60,000 worth of renovations on it, I think I can sell it for $200,000, right? Say they come to us with a loan like that, we need to make sure that sale price is reasonable in that neighborhood and for the property that they're describing. We need to, understand a lot of things before saying, okay, this is a loan that we're willing to fund. And again, one of the things that makes this tricky is that properties are unique, and fix and flip subject properties are especially idiosyncratic and weird. And professional appraisers, who are one of the experts that the ecosystem relies on, use recent sales of what's called comparable properties or comps to assign a valuation for the property. So if you say, hey, this property is $200,000, or it should sell for $200,000, an appraiser might look for sale records in that neighborhood around similarly sized or similarly aged properties and says, okay, that valuation sounds reasonable or it doesn't. And we've built a proprietary app to identify these kinds of properties. And this is really important for us to understand valuation in that neighborhood, to make sure that the comps picked by the third-party appraiser are sensible, right? So in this industry, it's really easy to commit fraud, right? If you have a buddy who's an appraiser says, hey, I'm going to submit a loan for, and I'm going to say it's a $500,000 property. I need you to submit an appraisal to the lender that backs up that property valuation. And it could be that these properties are only worth 300 grand, right? And then a scammer might say, oh yeah, I'm totally going to sell it for 500 and here's a professional appraisal. We want to be able to protect ourselves against that kind of thing. So we do things like we make sure that the investor can't pick their own appraiser, and then this app can compare the appraisal's choices versus what our algorithm says. So this is an internal app that kind of, it's proprietary. It runs inside our own internet portal. So it sources images from the appraisal, from property listings in the past, from Zillow, from Google satellites and street images. It gives the number of bedrooms and bathrooms, estimated sale price from all sorts of data sources. It has an interactive app where you can see, okay, these are the most comparable properties, and this is what the appraisal claims is comparable. So you can kind of check your answers to see if the appraiser's claims are reasonable. And you can also explore the neighborhood, right? I don't have any intuition, for example, for property values in, say, suburban St. Louis, right? But if using this app, I can quickly get a sense for, okay, this is what's popular in this neighborhood. These are the price trends and all of those things. So anywhere in the United States, we can do this. Involves hundreds of millions of properties, of course, and this is an app that we've built out. It also has features like you can choose which features are important to you. So you can say, oh yeah, I don't really care about the age of the home, but I do care that it has X, Y, and Z. And you can adjust for those weights and recalculate the comps. This is something similar that we've built. So doing real-time intelligence around ongoing events is really important. So this is an example that we just built over the weekend around the LA wildfires. So we can embed images and maps from news sources like the New York Times, and then we can draw our own polygon around the areas that we're concerned with. So a user can look at those 3 maps up top and say, okay, I'm going to draw this polygon, and then show us all the loans or pending loans that are in this neighborhood, right? We want to make sure that our properties are okay, and we want to know when an investor was in the middle of renovating a house, or we just funded a loan, and that house is now burned down, or it might be damaged in the future. So having live intelligence like this around these kinds of wildfire events or any sort of event like a hurricane, this is really important for our team as well. Again, not exactly AI at this point, but still very robust data intelligence tools. And as we build out all this, it's really important for us to restrict access to personally identifying information and other proprietary data. Right? We deal with property addresses, we deal with people's financial records and credit checks and background checks. We want to make sure that the AI is not making this information freely available even to our own employees. We have guardrails around AI use. We want to make sure that users aren't asking inappropriate questions or unnecessarily invading our borrowers' privacy. We want to minimize hallucinations, right? We can't have the AI say incorrect things about finances or anything. And ultimately, all of this is meant to enable human checks and accountability. It's not meant to replace human decision-making. It's meant to replace some of the more tedious or time-consuming things that people have to do. So in conclusion, we're building AI-augmented scaled workflows to handle really the most tedious manual tasks, like digging into these, page 78 or finding out if something's on page 78 or 79, verifying if something was signed, and so on. We're using both generative AI and more established data tools to generate and deliver, business insights in real time. We have to account for this really specialized business logic. We're in this intersection of private lending and real estate, and each of those are kind of idiosyncratic businesses. There's a lot of arcane terminology, and just you would not believe the insane document formats we deal with. And again, every loan, hundreds of thousands of dollars or many millions of dollars are at stake. So we need to be making the right decisions all the time. And we have to also be accountable for loan decision and we deal with the SEC, we deal with audits. So we have to be able to account for every decision that any tool that we use has made, including AI. And the goal here is to enable human work, again, not to replace it. So yeah, I'm happy to take questions. Again, apologies for the late start. I have a set of slides who I think a few folks in the audience are familiar with. Set of slides around basically slides to guide your thinking if you're considering that career switch toward data science or engineering. My email's right there, my LinkedIn and my Blue Sky handle are all right there. So please feel free to reach out.
All right, let's thank Taka real quick. We got time for maybe one or two questions. If you want to come up to the microphone, or if you raise your hand and we'll run a microphone to you.
Hi, Taka. It sounds like you're using a lot of off-the-shelf models. I was wondering if you were fine-tuning any of your models, like
Yeah, we're fine-tuning a lot of
system or
it.
whatnot, and maybe you can talk about that a bit.
Yeah, we're fine-tuning a lot of the models. We are using off-the-shelf or open source models, and we fine-tune them. We do a lot of prompt engineering. Some of our prompts read like novellas, to make sure that the AI has, has a vigorous set of directions. It's almost like a manual we give the AI. So that's right. We're using a lot of off-the-shelf and open source with a lot of tweaking and prompt engineering.
Other questions?
There was one in the Zoom, Jeff, from one of the speakers.
Go ahead and read it.
All right, I'm just gonna talk. You hear me all right?
Yes.
Yes.
Thanks, Taka. Just wanted to find out what your experience has been with using the RAG, basically, the internal document search. Because I know sometimes, as you said, it's like the hot thing, but then you do it, and maybe sometimes business stakeholders expect it to be like Copilot or like professional Chat GPT, and it just isn't, because it's supposed to be just for the documents. I wonder how you've kind of socialized that and how that's gone, how that effort's gone over the last year.
Yeah, I'll be honest that this is still a work in progress. The way I'm thinking about it is it suggests a list of basically bullet points and where the bullet points are sourced, and less about like giving prescriptive sentences around what the person was expecting. So maybe comparable to, it's comparable maybe to the AI searches in Google and less crappy.
Cool, thanks.
All right, let's thank Taka one more time.
Thank you.
Our next speaker is Eric Clausen-Brown, Principal Applied Scientist at Microsoft, also the co-chair of BACAC, which is the Beyond Academic Careers Advisory Committee, part of the AAS that I'm on as well. And he's going to tell us about how to build an NLP model to power an AI service. And we'll see if we can get out of this. Okay. And there. And that looks reasonable enough.
All right.
Hold on, why did you pause my screen share? Oh, I know why. All right. Stop, and we'll share again. All right, that was awesome.
All right. Thanks, everyone. By the way, Taka's podcast on Jeff's ATDS podcast is really good, so I recommend everyone go listen to it. In fact, just go listen to all of them. So I'm going to be talking about a cognitive service, which that's just a service that is provided to anyone who is willing to pay Microsoft, in my case, some money, that provides general purpose machine learning models. Extremely common text-based cognitive service would be a translation service. So you have some maybe English data and you want to translate it to Italian or vice versa. You would call that service and the service would pay you, or would ask for, some fraction of a cent per word translated. And that's basically the business model and the purpose of cognitive services. The particular cognitive service that I'm going to be talking about is a de-identification in a health context. So we're looking at like clinical data, and clinical data is very sensitive. And there are many people who have an interest in preserving privacy, including Microsoft itself. And there are a variety of reasons why you would want to use machine learning to de-identify that data. And I'll give some examples and explain that more. Oh boy. Okay, obligatory intro slide, which I think every single speaker here always gives. I got my PhD at Purdue University in AGN Jets. I did a 2-year postdoc in Germany at MPIFR. Halfway through that postdoc, I knew that I'd be transitioning.
Stay near the microphone.
Halfway through, thanks, Jeff. Halfway through the postdoc, I realized I wanted to transition to data science. So I started applying from Germany all the way to Seattle. In my case, I had a 2-body problem where my wife had a tenure track job in the Pacific Northwest. So, and so I made the transition about 10 years ago into the Seattle tech scene. I did 2 startups. One was an asset tracking IoT startup. That was my first job outside of academia. And that's where I just got basically familiar with writing production code, things like unit tests I was exposed to. Prior to that, I actually didn't have a great background that was very suited to data science. I had only written scripts that I used personally that were written in MATLAB. So, everything was new to me when I made that transition. The next place I worked at was a used marketplace, kind of like Craigslist. It's an app called OfferUp. And that's where I first got exposed to like high volume traffic in the context of a consumer app. This is an app that was getting like 10,000 requests per second. It's about a few million daily active users. So it was kind of also totally new to me. This is where I was, I think I started this job around 2016. This is where I was first exposed to natural language processing. So the app was highly like vision-based, like it had photos, but a lot of the machine learning we did was based on text, because text is smaller and more portable. It's easier to process, easier and faster to process, higher signal to noise, particularly back in 2016. So the next 2 jobs I've had have both been within Microsoft. The first one was in Azure AI Platform. This is the first time I actually worked on a code base that many, many people were contributing to. I had never, prior to that, I think the code bases I was working on, maybe 2 to 4 other people were contributing to. This was, I think there's something like 40 engineers that were contributing here. So I learned here the value of unit tests as a way to like defend the code that you're writing so that other people don't break it. There's a lot of interesting things I learned here in this group. And then the kind of group that I'm in now that I joined right at the beginning of the pandemic was basically it's the group that has the public-facing product called DAX Copilot. Microsoft has like 1 million different products. All of them are branded Copilot in some form. It's just a product that is sort of ChatGPT-like, essentially. And in particular, I've been focusing on health text de-identification in the last few years. And then, also in the last year or so, I've been working with Jeff on the Beyond Academic Careers Advisory Committee. So if any of you have opinions about what the AAS can be doing for you to transition to industry, please speak to me or Jeff. Okay, so what is health text de-identification? So all it does is it detects and redacts or surrogates personal health information. PHI is the acronym that everyone uses. A more common acronym that you use generally for identifying information is PII, personal identifying information. So the example here, which I'll just be picking on Jeff, is imagine that there's a little snippet of clinical text that says Jeff had right shoulder pain on January 14. What the service does, if you want to redact, is it just replaces Jeff with something like patient, some label for that kind of entity, like a name of a patient. And it would also replace date in this case. So there's a number of different types of what we're called named entities, like patient date, and our service supports something like 20 of them. And many of these entities fall under like the HIPAA regulations within the United States. However, we do pretend, at some point we would like this service to be international, so it's not necessarily tied to HIPAA, but it's let's just say strongly informed by it. So why exactly would you want to be using health de-identification? I'm sure you can kind of imagine why, but in particular, there's a couple different reasons. First, let me just start by saying we are using machine learning to de-identify, and no machine learning model will have 100% accuracy. So usually in the context of privacy, you want to have at least in particular scenarios of interest, 100% guarantees that your data is private. So why would you want something that's just 98% certain secure? So the answer is that it's, in many cases, just risk reduction. It's 2025, we know that data can easily be hacked. And if data were to fall into a hacker's hands, it would be good if it were de-identified, or it'd be better if it were de-identified than if it were not de-identified. So it's just risk reduction. It's not risk elimination. And then finally, it is 2025, and everyone is interested in generative AI. And generative AI has unique issues with privacy. So a really fun paper that came out from Google DeepMind a year or two ago. It's this kind of sophisticated paper about privacy in the era of LLMs, but the headline of this paper was not a sophisticated analysis at all. It was someone had figured out how to hack ChatGPT to get it to spew out its training data. And the hack is bizarre. The hack is shown in this green box here, or no, in the blue box. And all you needed to do, like a year or so ago, I'm assuming it's been fixed, is say, repeat this word forever, poem, poem, poem. So there it is. The geniuses at Google DeepMind have hacked ChatGPT in this way, and then ChatGPT just emits all of its training data. So if ChatGPT is trained on data that is has sensitive information, this is kind of a new way, a new vulnerability that's at play. And so if you are going to be training or fine-tuning your generative AI model on data, you need to think about this. And a common way to mitigate this risk is to first de-identify your data. And in particular, you'd want to, in this case, surrogate data. So you'd want to say, instead of like Jeff had right shoulder pain on January 14, you'd want to say, replace Jeff with some surrogate like John, and replace the date with some relevant date, which I'm not going to talk a lot about surrogation here, but it is a very hard problem to surrogate data appropriately. Because when you do surrogate data, it has privacy guarantees that are even better than redaction. And the main way to describe it is it quote, gives your de-identified data the property of hiding in plain sight. Because if your system is 98% accurate, say 2% of names are not surrogated, but all the other names are, then they're not going to stick out like a sore thumb. So if Jeff is surrogated a bunch of times in the document with John, but then in one place we missed it and it just says Jeff, it's not going to stick out like a sore thumb, and it's going to be harder to identify. So there's a million and one reasons why surrogation is good, but to have a good surrogation system that hides in plain sight well is difficult. Okay, so our goal here, I'm supposed to be telling you how to build a text-based cognitive service. How do we start building our PHI detector? First of all, it's 2025. Can't we just use GPT-4? And the answer is yes. Of course we can use GPT-4. It's not bad. However, GPT-4 costs a lot of money. It's of order right now 1 cent per word. And many people want to de-identify large data sets. So if you're a large customer, every day you might be wanting to de-identify tens or hundreds of gigabytes of data. And you are not going to be using ChatGPT to do that. So it's too expensive. It's also not just expensive in terms of money, but it's also expensive in terms of time, because just the latency to de-identify a document of 1,000 words or so. It's probably of order like 20 seconds now, maybe. So we need smaller, more efficient models that are going to be fine-tuned on this task, that are fast and cheap to run, and that you can, are reasonable cost, reasonable price to, use to de-identify a terabyte of data or something like that. So that's kind of where we start, kind of small models. And then you also cast this as a traditional machine learning problem. The traditional machine learning problem here being named entity recognition. I think I've heard it like multiple times on Jeff's podcast, including I think the most recent one, where someone was talking about using this at Twitter for moderating content. This is an extremely common thing to do. And all it is a model that reads text and classifies every single word into a few categories. In this particular case, which I just stole from the internet, it's translating a bit of text about Steve Jobs and Wozniak and Apple into entities like person, company, product, date, things like that. So, and I say classify every single word. The words that are not highlighted in named entity recognition, these are classified into the other class, and they're what you ignore. So that's what the task is. And so this, I don't know how old this task is when someone first defined it. It was probably in like 1956 or something like that. And we've gone through quite a few different generations of models. But since 2018 or so, everyone has been using deep learning and transformer architectures like BERT. These are cousins of ChatGPT that are much smaller and efficient to run. Okay, so that's our task. So we need to think about building a machine learning model. The next slide is also kind of an obligatory slide. I think everyone has a slide comparing astrophysics to their day job these days. So this is my attempt at that. So I'm going to say the way I'm couching this is that it really starts like any project that you'd have in astrophysics. I think it ends differently. Although I'm going to make this dichotomy, but I am 100% sure that there are in fact many astrophysics projects that have some even more similarities to industry projects. So the first part of the project, which I have all kind of smushed together into one slide or one bullet point here, and it's probably the part you need to spend the most time about, is you're of course thinking about your goals, you're hypothesizing, and you're beginning to collect data. I think astronomers are also really good when compared to other scientists from disciplines, et cetera, at thinking about biases. I mean, even to the point where astronomers do a nice job of modeling biases. The next thing that in many astronomy projects you would do, or in industry, is you train your ML model on the data, except in astronomy you use just a little different words. You use the word fit, and oftentimes it's not a machine learning model you're using, it's some sort of physics-based model. And so that kind of part of the workflow is pretty similar. The parts that are a little different are on the astrophysics side. One of the things you're worried about a lot is, are you fitting noise or are you overfitting? Overfitting is a concern within machine learning, but it's different than in astrophysics. In astrophysics, if you're fitting noise, then your fitted parameters are not going to make a lot of sense. And a lot of times you're putting a lot of work into interpreting your fitted parameters. In machine learning, you are not interpreting your fitted parameters almost at all. And in many contexts, we do not care if we are overfitting the model. The only thing we care about is how well the model performs on held out data. So again, even with machine learning, there are contexts where people talk about overfitting being bad, but at least in the sense of your model performing well on held out data, that's all we care about. Your model could memorize what it was fitted on. It could, so to speak, have a little squiggly line through all of your training data, and it would look terrible. And as an astrophysicist, you might want to puke when you see that. It does not matter in machine learning. There are fields of machine learning where we want to do interpretability, where we really do look at the model and weights, but as a rule of thumb, we don't care about that. So the next thing you ask once you've already kind of fitted a model is also kind of different. So in astrophysics, oftentimes you're asking, is your physical model right or wrong? Or do you need to add some more complexity to it? In machine learning, you are not asking that question at all. You're not interested in some sense, you're not interested in the truth. What you are interested in is whether your machine learning model is good enough. And this is actually when I mean, a lot of software engineers are interested in machine learning, and they will come to me and the first question, I think almost every person at Microsoft or other companies I've worked at has asked me is, when is your model good enough? Like, what accuracy threshold? Is it 90%? Like, I've had people just with no context for what the machine learning model will be used for ask me, is 90% good enough? Or is it 95? And of course, there is no right answer to that. There are well-known baselines that you will use in every project. For example, instead of using your machine learning model, you just say, what would what if we just randomly choose things or randomly choose numbers, or every number we predict is the same thing? These are well-known baselines that people use for many different projects. And in many cases, as long as your model beats them, it might be good enough. If it's better than things were before, then your model's good enough. So that's something that's really different. The other thing, okay, so in astrophysics, I already said this, but the output of this whole process is oftentimes interpreting individual fitted parameters. This is not always the case. I understand that, but in many cases, your fitted parameters are, like some of the main results of your paper and have physical interpretations. In machine learning, there's a lot of other things that we're doing frequently that you might not do in astrophysics. Oftentimes, your model might not be good enough, and you're analyzing, well, where is it falling short? And there's particular scenarios where your model is falling short. It might be doing better than random, but we know maybe there's some scenario that we want the model to cover. In this case, very frequently, especially in 2025, you're going to synthesize data for it. It's very easy to synthesize data because we have these wonderful generative models, whether it's vision or text. And this is something we all rely on heavily. It is hard to synthesize good data. When you use a LLM to do this, to generate an interesting data distribution, it is hard. One that has a nice amount of diversity, isn't just kind of repeating itself over and over, but maybe making trivial changes. It is a real skill, and there are papers on how to generate these synthetic data sets. Where am I? How many do I have? How many minutes?
-2.
-2?
Well,
okay.
Taka started late.
Okay. Well, let me just switch over to what metrics that we're trying to optimize for. Apologies that I have to skip all of this. So the metrics that we're trying to optimize for, which map onto real kind of arguments with different groups who are using our model, is what we're trying to do is we're trying to, on the one hand, reduce the number of false negatives. So this is where Jeff has right shoulder pain. If our model does not label Jeff, that's a false negative. We should have been labeled Jeff as a patient. So that kind of metric is recall. We want to optimize recall. So this kind of metric is the kind of metric you want to focus on if you want to preserve privacy. However, if you're stupid, you could just redact the whole document and you could have a perfect metric along these lines. So of course, no one is stupid, no one would do that. And so the other metric to make sure we don't do that is we want to reduce false positives. This is where the word "the" might be labeled as patient or something like that. So that's also something we want to not do. And the metric associated with this is precision. And so within machine learning, this is like machine learning 101, which I'm sure many of you have heard of. There's just this precision recall curve. And the precision recall curve in our particular use case has two interpretations. If we want to maximize precision, which is at the top left, these are the kind of people who want accurate data. They don't want to have a bunch of surrogates which are obscuring important clinical information. These are people who maybe they'll be training a model on this data and they want that model to be accurate. And that is a good thing. I mean, in many cases, there are ethical reasons for why you want your model to be accurate. On the other hand, on the other side of this curve, on the bottom right, where we have high recall, these are people who want to preserve privacy. And so again, you have ethical implications for wanting to make sure that no names are leaked or that a generative model might not emit that piece of PHI. So this is kind of the fundamental dichotomy that we, as a cognitive service, are constantly dealing with all these external stakeholders who care about these metrics differently. And it's kind of an interesting problem to try to ship something that pleases everyone. Thank you very much.
Thank you. We have time for 1 or 2 questions. For those on Zoom, you should have access to the Q&A feature, and Ava will keep an eye on that and let us know if there's a question there. But in the room, I saw a finger or a hand. Okay.
Hi, very nice talk. So I had a very basic question, I guess. So if you compare with like astrophysics or like any physical research, so we kind of try to make sense of the parameters that we feed, like in a physical sense. But for machine learning models, like about the parameters or like hypertuning or whatever, so how do you try to make sense of them in terms of like what they physically mean? Yeah.
Yeah, many times we don't try to make sense of them. What we try to do, so you're frequently in astrophysics, you're fitting a model for the purpose of deriving fit values, and then you put interpretations on them. In machine learning, you're using the predictions of that model for, in the case of a cognitive service, to translate text in the future. And the particular values are not very important. Now, you might want to then, might want to look at those values if you're effectively debugging your model, and your model is, let's say in training, it just kind of goes crazy and the loss like spikes. Then you're thinking, well, what's going on with this model? Or, do I need to do something with the loss during training? And maybe you need to reparameterize. That's when you start to think about the model, but that's kind of the only case that you do that. And I will say, at least in my experience, it doesn't happen that frequently.
But you kind of do feature engineering or other kind of things. So
Yes, the inputs and the outputs are life here. It's the black box in the middle. It's not really a black box, but it kind of is a black box. The black box in the middle is the bit that you're not, that's the machine learning model. That's a tree or a neural network. It's a network that has 60 million parameters or one that has 100 billion parameters. There is a very particular field for people who do pay attention to that. And one of the names that it has is mechanistic interpretability. And it's hard and it's interesting, but it's not done by everyone.
All right, I want to stop us there so we make sure we take a quick break. So let's thank Eric again, and we'll be back at 10:25.